The following presentation is about limits. The limit is the value that a function approaches. Say we have the problem, the limit of x approaching 1 of x squared minus 1 over x minus 1. We can determine the limit using a variety of methods. The first is algebraically. So if I factor the numerator and canceled out like terms, I'm left with the simplified version of the original function, the limit of x approaching 1 of x plus 1. When I plug in the value of x plus 1, I find that the limit of the function is equal to 2. We can also use a graph to find the limit of the function. When I graph this function, I have a linear relationship with a hole at 1, 2. But I notice that the function approaches 2 from both the left side and the right side of x equals 1. So since the limit of the left side of the function is equal to the limit of the right side of the function at x equals 1, the limit exists, and that limit is 2. Finally, I can use a table. I set up a table of values that includes x equals 1 and numbers slightly higher than x equals 1 and slightly lower than x equals 1. And even though I have an error when I plug in the value of x equals 1 into the original function, I notice that the numbers to the left, slightly less than 1, is approaching 2, and the numbers slightly greater than 1 is also approaching 2. So therefore, the limit exists, and the limit is equal to 2. Graphing a piecewise function. Let's say we wanted to find the limit as x approaches negative 1 of f of x equals negative x plus 1 when x is less than negative 1, and the square root of x plus 1 when x is greater than or equal to negative 1. So when we create the graph of the piecewise function, I'm going to start with the left side of the graph. I know that my function is going to look like negative x plus 1 when the x values are less than negative 1. So I create a table, plug it into my linear function. I'm going to do the same for the x values that are greater than or equal to negative 1. So I created a table. I chose values that I knew when I plugged in to my function I would be able to take the square root because graphing decimals is a little tricky. Plugged in the values. Then we have to decide, what do you graph at x equals negative 1? I know I have an open circle at negative 1, 2 because of the less than symbol, and I know I have a closed circle at negative 1, 0 because of the greater than or equal to symbol. So when I graph this function, the limit as x approaches negative 1 of f of x does not exist because it is approaching different values from the left side of the function and the right side of the function. Here's some more techniques for finding limits. First is direct substitution, which means plug in a value. You're always going to want to start with this method first. If this method fails you, you can use cancellation, which is simplifying or canceling out terms. Rationalization, which is multiplying by the conjugate to eliminate the square root. And we can always use a calculator to plug in x values near the value we are trying to find the limit of. A limit is reachable if the limit exists and there are no holes at that location. The limit is unreachable if the limit exists but there is a hole at the location. Here's the first direct substitution example. So again, direct substitution means plug in the value. The limit as x approaches 2, x squared plus 2x minus 3. When we plug in that value, it comes out to 5. So the limit as x approaches 2 of x squared plus 2x minus 3 equals 5. We use direct substitution. There's no hole at our x location, therefore it is a reachable limit. Direct substitution with a piecewise function. So since we care about the limit as x is approaching 1 of our piecewise function, 4 minus x when x is less than 1 and 4x minus x squared when x is greater than 1, we're going to use direct substitution. We're going to plug in 1 to the left side. We're going to plug in 1 to the right side. But we need to always check our domains. When we check the domain, we realize that there's a hole since neither x value is equal to 1. So for the first left side, the hole's at 1, 3, and the right side, the hole's also at 1, 3. If the limit of the left side equals the limit of the right side, then the limit exists. In this situation, the limit as x approaches 1 of f of x is equal to 3. We use direct substitution. There is a hole at 1, 3, therefore it's a non-reachable limit. Here we have another direct substitution problem. When I plug in x equals 2 into 5x over x minus 2, I get 10 over 0. This limit does not exist. The limit does not exist when you substitute and you get any number over 0. But if you get 0 over 0, you need to use a different method. So cancellation is one of our options that we can use. The limit as x approaches 1 of x cubed minus 1 over x minus 1. When we go direct substitution, we get 0 over 0. This does not mean does not exist, so we're going to try to cancel out. I notice that the top is the difference of perfects cubed, so I'm going to break that down into x minus 1, parentheses x squared plus x plus 1 over x minus 1. Cancel out the terms. I notice that there's a hole at x equals 1. I'm going to use direct substitution in the remaining quadratic. The limit as x approaches 1 of x cubed minus 1 over x minus 1 is equal to 3. We use cancellation. There's a hole at x equals 1, 3, and it's a non-reachable limit. Rationalization. We're going to use this whenever we have a square root function. So I have the square root of x plus 1 minus 1 over x. When I use direct substitution, I get 0 over 0. I'm going to multiply by the conjugate. And what the conjugate is all you have to do is switch the sign in between the first term in your binomial and the second. Since I have the square root of x plus 1 minus 1, I'm going to multiply both the numerator and the denominator by the square root of x plus 1 plus 1. And after we FOIL and cancel out and simplify, we are left with the limit as x approaches 0 of x over x times the quantity x plus 1, square root plus 1. Cancel out. There's a hole at x equals 0. Plug in 0. The limit exists, and the limit is 1/2. We use rationalization. There's a hole at 0, 1/2. Non-reachable limit.